Hello everyone, I'm Reza, founder of the Optimization City. Welcome to our course on Primal Simplex Method. This course is designed to provide a comprehensive understanding of the Primal Simplex Method, which is widely used for solving linear programming problems. The Primal Simplex Method is an iterative algorithm that starts from the initial feasible solution and moves toward the optimal solution by improving the objective function value at each iteration. It's a powerful tool for solving a LP with a large number of variables and constants as well. In this course, we will learn the fundamental concepts of the primal simplex method, including the basic algorithm, initialization, pivot rule, and termination criteria. We will also solve the variety of LP model using the primal simplex method. Our course is designed for students, researchers, and professionals who want to learn and apply the primal simplex method in their work. This course is designed to provide a comprehensive understanding of the primal simplex method and its variation. Here is a summary of the topic we cover here. First, basic of the primal simplex method. We will start by review the basic of the LP modeling, a slack variable, basic, and basic feasible solution. In the second part, we will dive into the primal simplex method itself. We will cover the basic algorithm, initialization, pivot rule, and termination criteria. We will explore the special case that can arise when applying the simplex method, including degeneracy, unboundedness, and infeasibility. In some cases, it may be necessary to use the two-phase method to find the initial feasible solution before applying the simplex method. We cover how to apply the two-phase method in phase 1 and phase 2 in this section. The revised simplex method is a more efficient version of the simplex method. We will cover the basic algorithm, initialization, pivot rule, and termination criteria for the revised simplex method. Simplex method with the bounded variable is the sixth part of this learning course. Sometimes the variable in the LP model are bounded, meaning that they have upper bound or lower bound. We will discuss in this section. And finally, we will provide a set of exercises to help you applying the primal simplex method to solve the LP model. We will provide a linear programming problem with the solution and a step-by-step solution process to help you check on your work and build your skill. By the end of the discourse, you will have gained a solid understanding of the primal simplex method and its variation, and we will be able to apply them to solve a wide range of linear programming. We hope to find this course informative and useful in your study or work. So let's get started. The primal simplex method is an algebraic method used to solve the linear programming problem. It's easier to work with equations that are equal rather than inequality. So the first step of this method is to convert the functional constraint from an equal form to an equal one. The constraint of the negativity can remain inequality to an equality. Can remain on equality because they don't directly affect the solution process. To convert an equality to an equality, we introduce slack variable. To demonstrate how the simplex method works, we solve an example. Here, we have 3 constraints and 2 variables. We are going to maximize 3x1 plus 5x2. So let's look at the first constraint. x1 is less than 4. We can define the slack variable x3 as a difference between right-hand side and left-hand side of constraint 1. This allows us to write constraint 1 as an equation that's equivalent to original constraint. As long as as long as x3 is greater than or equal than 0. This gives us the following set of constraints. So we added 3 variables to become the inequality constraint to equality constraint. To help illustrate this concept, let's consider the simple example. If we have constraint 1, x1 is less than 4, x1 has a value of 1. If x1 is the value of 1, then the slack variable would be equal to 3 because summation of x1 and x3 would be 4. We can rewrite the constraint as the x1 plus x3 is equal to 4, which is equivalent to x1 is less than 4 when x1 is 1 and x3 is 3. This process can be applied to other inequality in these constraints. We have 2 other inequality constraints, which allow us to rewrite the entire model as necessary. We will discuss in future. We call x3, x4, and x5 as a slack variable. Model MP1-1 is essentially the same as the model P1, but it's been simplified to make a algebraic operation easier. In P1-1, there are 5 variables and 3 constants, which means that there are 2 degrees of freedom. It means number of variable minus number of constants. To solve the system of equation with 3 variable and 3 constraint, we will set the desired variable for 2 additional variable in each step. In the simplex method, these additional variables are set to 0. Variables that are set to 0 are called non-basic variable, while the other called basic variable. The solution where all non-basic variables are equal to 0 is called the basic solution. And the basic feasible solution is the basic solution where the basic variables are non-negative, that we call basic feasible solution. We will use this term in future, more common. In this model, we can easily identify the basic variable because each equation has only one basic variable with the coefficient of 1, and this variable does not appear any other coefficient. So we can see that x3 is the basic variable and does not appear any other coefficient. To simplify the process of solving the problem, it's helpful to rewrite the objective function as a functional constraint and add it to the list of constraints with the row of 0. Before introducing this simplest method, we rewrite the problem P1-1 in this way. So we have P1-2 is a final model for entering the Primal Simplex model algorithm. Primal Simplex method is a formal method used to solve the LP model. At each step, the method aims to find a basic feasible solution that's either equal or better than the previous solution, ultimately leading to an optimal basic feasible solution. To move from one basic feasible solution to another, we simply need to convert a one basic variable to a non-basic variable, which call the leaving variable, and a non-basic variable to a basic variable. It's called the entering variable. This will move a current basic solution to adjacent basic feasible solution. If the basic feasible solution is better than all of its adjacent solution, it's the optimal solution and algorithm will be end. This is all we need to solve the LP model with the Primal Simplex method. So we have the A general summary of this step involves the primal simplex model in this figure. We will discuss this process with more detail in the following slide. What is the initial step? To illustrate each step of the simplex method, we will use an example. In the initial step, we set the slack variable x3, x4, and x5 as a basic variable, and the non-basic variable are x1 and x2 to 0. To simplify the calculation, we will use a table called simplex tableau, which show the coefficient of the variable and the value on the right-hand side. The coefficient of the variable in the objective function and the functional class constraint and right-hand side, which show the coefficient of the variable and the value of the right-hand side. The simplex tableau for our example are here. Since each equation contains a basic variable with the coefficient of the +1, the value of each basic variable will be equal to right-hand side. So this is the basic variable of the first row, and this is the value of the basic variable here, x3. The basic feasible solution for the table above is x1 is 0 because it's a non-basic variable, x2 is 0 because it's a non-basic variable, x3 is equal 4, x4 is equal to 12, and x5 is equal to 18. For simplicity, we show any basic solution as follows. To determine if we have reached the optimal solution, we check it all coefficient either row 0 of the simplex tableau are non-negative, greater than equal than 0. If they are, then the current basic solution is optimal and we can stop. If not, we repeat the iteration. So in this tableau, we can see that we don't have the positive value for the coefficient of the non-basic variable. So we should continue the process. What is the iterative step, which is most important part of the simplex methods? We do the following sub-step. We select the non-basic variable in row 0 with the largest negative coefficient as the entering variable. This variable will cause the fastest growth rate of the objective function. We draw a rectangle around the column below entering variable and call it the pivot column. In our example, x2 has the largest negative coefficient, -5 here. So it's selected as an entering variable. We write a blue rectangular under the x2 we call pivot column. In substep 2, we determine the leaving basic variable by following this step. Consider the positive coefficient in the pivot column here. We have 2 positive value. Divide the value of the right-hand side by the positive coefficient here, 12 by 2, 18 by 2, and select the row with the smallest value. So this is the second row has the smallest value because it's equal to 6. The basic variable of this row would be leaving variable. So this is the leaving variable. This is the input variable. And we call this rectangular is a pivot row. We draw a rectangular around this row and call it a pivot row. The value at the intersection of the pivot column and pivot row call it the pivot number. So you can see the pivot number, pivot color, and pivot row. In this tableau, the entering variable is x2 and the leaving variable is x4. To get the new basic solution, we need to create a new simplex tableau using the following step. In column 0, replace the leaving variable x2 with the entering variable x2. So here, so we just replace x2 by x4. To convert the coefficient of the entering variable to 1 here, divided the pivot row by pivot number. So we divide this row by 2. Remove the basic variable from the other row. We need to make the coefficient in the pivot column 0, except for the pivot number. So you should remove here. You should replace -5 by 0 and 2 by 0. In order to do this, we should do the following. Multiply the pivot row by the non-zero constants that will make the coefficient of the pivot column, except from the pivot number, become 0. So you should just multiply this row by 2.5 and sum with this row. And add the multiple of the pivot row to another. So you can see that we had to multiply this row by 2.5 and plus this row. After creating a new simplex tableau, we check the stopping condition. If it is met, the algorithm step. Otherwise, we go back to the iterative step. We repeat. So we repeat this operation until we have the termination condition. In this tableau, you have all you need to have the optimal solution. We have the 3 iterations. First iteration, you have x2 is the entering variable and x4 is the leaving variable. In the second iteration, x1 is the entering variable and x5 is the leaving variable. In the third iteration, you can see that the 0, 1 would be positive. So we have the termination condition met, and this is the optimal solution. x3 is equal to 2, x2 is equal to 6, x1 is equal to 2, and the objective function would be 36. Note that at each iteration of the simplex method, we test one of the corner point of the feasible region. Since the model is small, you can observe the movement of the corner point of feasible region through the iteration of the simplex method. So here we have the 3 iteration to go to the optimal solution. In the first iteration, you are in this point. In the second, you are in this point, and in the optimal solution, you go to this point. So as you can see in the simplex method, we just check the corner point of the feasible region. In this example, if we had not chosen the variable with the larger absolute negative coefficient, which means x1 as an entering variable, we would have moved counterclockwise in the feasible region. So if you pick another example here, another variable, so we move from the other way to go to the optimal solution. So in the following, we discuss important definition of the simple in the linear program, which is very common, which is used very common in the industry. What is shadow price? The simplex method provides the variable information in addition to the optimal solution. The shadow value of the source I, denoted by yi star, measure the marginal value of the source I and indicate the rate of increase of width due to the slight increase in the right hand side of the source I, which is bi. However, the rate of increase must be small enough to maintain the current set of the variable as optimal, because any change to the basic variable will also change the shadow price. So the shadow price of the ith constraint here, the ith constraint is determined by coefficient of the ith slack variable of the that constraint in row 0 of the final simplex method. So we can find the shadow price by doing this. For example, in model P1, the shadow price of the constraint 1 is equal to coefficient of the x3 in row 0, which is 0. So this is the final table of the P1 model. X3 is a slack value of the first constraint. So the shadow price of the first constraint is equal to 0. X4 is the slack variable of the second constraint. So the shadow price of the second constraint is 1.5. And X5 is a slack value of the third constraint. So the shadow price of the third constraint is equal to 1. In other words, the shadow price of the source 1 represent the maximum price of the that cost effectiveness to pay for increasing 1 unit of the that resource. So it means if you are a manager of any company factory like this, you should pay maximum the shadow price for increasing 1 unit of the source. So it's very important. Let's go to the next section. In this section, we are checking some special cases in simplex method. First one, the picking the interim variable. There are some special case, so we speak in this section. When multiple non-basic variables have the largest negative coefficient, this is the one of the special cases. In this case, we pick the one with the largest index. For example, in P1 model with the different objective function, we change the objective function by this. Both x1 and x2 have the coefficient of 3. We would pick x2 because it has the larger index. So the index of the x1 is 1, the index of x2 is 2, so we just pick x2. If we had picked x1 instead, we would have reached the optimal solution after the 3 iteration, whereas choosing x2 would have allowed us to reach the optimal solution with the only 2 iteration. The degeneracy occurs in the linear model when the one basic variable takes on a value of the 0 in the basic feasible solution. This can cause cycling in the basic solution and slow down the simplex method, making it efficient in practice. So it's very important degeneracy in the practical. To get out of the degeneracy, we can use the blend rules. These rules select a variable as an interim variable that has the lowest index and the lowest coefficient of the objective function. If there is more than one choice for leaving variable from the basic variable, we select the variable that is closest to the objective function line or row 0. Unbounded. If none of the basic variable have leaving condition and the value of the entering variable can increase infinitely without any of the other basic variable become negative, the value of the z is unbounded. This situation occurs when the coefficient of the pivot column in the simplex table are negative, are non-positive, or negative or 0. To clarify this issue, consider the following model. Okay, the graphical representation of the above model is shown here, so you can see that the value of the objective function increased infinitely. The simplex table for this model is given here. And in the above table, we see that the x4 is equal to 12 plus 2x2, and x5 is equal to 18 plus 2x2 minus 3x1, where x2 can be increased infinitely. As a result, the value of the objective function increased to infinitely, and the constraints do not prevent the unboundedness of the objective function. If this happened, it could be due to the miscalculation or missing any constraint. So here you can see that the column, the pivot column behind the x2 is a negative or 0. So it showed that this model unbounded. If the problem has a more than one optimal solution, at least one of the non-basic variable will have the coefficient of the 0 in final row 0 in the simplex method. This means that increasing any such value will not change the value of the z. Therefore, we can identify the other optimal solution by performing the additional iteration of the simplex method, each time selecting a non-basic variable with the 0 coefficient as an entering basic variable. To illustrate this, consider the following model, and you can see the visual representation of the model above in picture here. The line between 2, 6 and 4, 3 has many points, and each one is the best one you can get. Whenever, which one you want, it doesn't matter. Since the mathematical model cannot consider the all economic factor in the real world, in this case, you have many solutions. You may need an expert to help to choose one of them. So what happened in the simplex methods, in the simplex table? As you can see in the table here, two basic solutions for this table and for this table are the best solution with the optimal value of the z is equal to 18. You can see that the terminal condition for simplex method happened for this table and for this table. The fact that at least one of the non-basic variable has the coefficient of the 0. So in this table, you can see that the coefficient of the x3 as a non-basic variable is equal to 0, and the coefficient of the x4 in this variable as a non-basic variable is equal to 0. So it's when it happens, you have the multiple optimal solution. Whenever you have an equality constraint, you can replace it with a pair of inequality constraint. However, this will increase the number of constraints, will not always convenient for solving a linear program. Instead, you can use artificial value techniques, which we'll explain in the following example. Consider this example. The only change that occurs in the linear program model in this example is that the third constraint here become equality constraint. So the new model will look like this, and we can have the visual representation of the model here. So you can see that the feasible region is a line rather than the space. Unfortunately, this equation do not have an obvious initial basic feasible solution because there is no slack variable to use an initial basic variable for constraint 3 here. So you can see that you don't have any slack variable to pick as the initial to pick as the basic solution. So you need to find an initial basic solution to begin the simplex method. What we can do? Here, one way to overcome this difficulty. To get an initial basic feasible solution, you can create an artificial value variable as x5 bar. You can do this by making two change in the original model. Add an artificial value, call it x5 bar to constraint 3 and make sure it's not negative. So it means it's not negative constraint. So the new constraint will be here. And this model would be as a follow. And you can see that the third constraint has a basic variable. So what happened when you add an artificial variable x5 bar, it increased the feasible region, which is similar to figure below in the first model in the discourse. So surely it's completely different from this feasible region. The next step to penalize having the x5 bar is equal to 0 by modifying the objective function as here. So in order to make this feasible region to this feasible region, we should do following. So we have the objective function like this, where m represents a very large positive number. This method of the ensure x5 bar in the optimal solution is known as the big M method. It's very important in the simplex solving the model with the artificial variable. Before you can apply the simplex methods, optimality test, or find the entering basic variable, you need to make sure that all basic variables are eliminated from equation 0. However, the system of concern is not yet in proper form because the basic variable x5 bar has a non-zero coefficient in row 0. So here, this is a basic variable, but it has a coefficient in the row 0. So to eliminate x5 bar from the row 0, you can subtract m times of row 3 and to subtract m times of b from a. So it means in the other way, you times row b by minus m and sum with or add with row 0. By doing this, you have the new row 0. So the x5 bar has 0 in this row, which is the row of the objective function. By doing this, you can find the optimal solution for the original model by using the simplex method on the modify problem, starting with the initial basic solution this. So you do the following, the traditional way of the simplex method, and finally you can see that you have the optimal solution. X1 is equal to 2, x2 is equal to 6, and x3, x4 and x5 bar as well is equal to 0, and the objective function is equal to 36. The big M method is commonly used to solve the linear programming model with the artificial variable. However, it can be challenging to calculate the big M in a large model, and it may lead to computational error. In such case, the two-phase method is recommended. This method involves a two-phase. In phase 1, we aim to minimize the summation of the artificial variable. If the sum of the artificial variable becomes 0 by the end of this phase, this solution is used as the initial basic solution for phase 2. In the next example, we apply the two-phase methods. Let's work through the simplex method step by step using the two-phase method for solving the following problem. We have the 4 decision variable and 2 constraint. We can write the model in the standard form as follows. We add the 2 slack variable x5 and x6. Next, in the two-phase method, we solve the model that minimizes the objective function. W is the summation of the slack variable x5 plus x6, subject to constraint of the original model. Essentially, we are trying to optimize the following model. In the phase 1, you can solve the above model and the original model simultaneously by entering the objective function W for phase 1 and Z for original model in the same simplex table as follows. This is the simplex method. In the first table, x5 and x6, which are the basic variable, do not have the 0 coefficient in the row 0. So we do the elementary operation like the big M method to make them 0. Then the table is ready for simplex method by objective function W. Here is the final table in the phase 1. We can use this basic solution in this table for starting the phase 2. You can see that it's difficult to find such solution at once. With this basic feasible solution, we do the phase 2 and then reach the optimal solution for phase 2, which are the optimal solution for original problem. So this is the optimal solution for the original problem, which is x1 and x2 is equal to 0, and x3 and x4 is equal to 50, and the other is 0. Let's work to the general form of the simplex method, which is called revised simplex method. The revised simplex method is another practical way to solve the linear programming model. While the simplex method is suitable for manual calculation, it may not be efficient enough to solve the large problem using the computer. This is because it stores information that may never be used in a simplex iteration. For example, some variable may never meet the necessary condition to be selected as the input variable, meaning that all calculation related to the coefficient of those variable in the objective function and constraint will unused. In other words, the column corresponding to that variable is calculated but is not actually used. The revised simplex method used the all principle and step of the original simplex method to solve the problem. However, it avoids performing a redundant operation and storing the useless information that would require a lot of memory on the computer. To apply the revised simplex method, you need to use a matrix formation. This makes it necessary to define the metric formation of the LP model. To represent the standard linear programming, we use the matrix as a follow. Let's see the following model as a matrix. So we are going to maximize z is equal to c times x. A subject to a times x is less than b bar, and x is non-negative, where x is a vector including the x1 till xn, c is a vector as well, c1 to xn, a is a matrix that includes the coefficient of the variable for the functional constraint, and b bar is a vector that includes the right hand side of the constraint. In this example, we write a model as a matrix representation. So x is a vector including x1, x2, and x3 as a 3 decision variable. C is the coefficient of the decision variable in the objective function as a vector. A is a coefficient of the variable in the constraint as a matrix 2 row and 3 column. And b bar is the right hand side of the constraint. So we are going to maximize c times x. In the case of adding a slack variable, the problem becomes as a follow. So we have s as a slack variable as a vector including s1 to sm. M is a number of variable. So a comma I is a matrix that show here that all zero except from the diagonal. Okay, it's equal to 1. So this is the matrix representation of the model with the less than model, with the less and equal equation. So this is the general form of that model if you want to add the slack variable. Here, let's see more. Let's talk about this model a little bit more. After adding the slack variable s, you can display the model as a follow. The number of basic variable is the same the number of the constraints. So we have the 3, we have the 2 slack variable, and we have the 2 constraint here. Okay, which is m is equal to 2 in this case, and a comma I has the m row excluding the non-negative constraint, and m plus m column including m basic variable and n non-basic variable. In this example, m is equal to m and n is equal to 3. The matrix A comma m is divided into 2 matrices. One consists of the coefficient of the basic variable, and the other consists of the coefficient of the non-basic variable in the constraint. So this is the coefficient of the basic variable, and this is the coefficient of the non-basic variable in the constraint. The matrix of the basic variable coefficient is represented as a b. This is b, and this is n. And is a matrix of the non-basic variable coefficients. Similarly, all variables of the problem, xj and si, are divided into two groups: basic variable, which are s1 and s2, and xn, or non-basic variable, which are x1, x2, and x3. Let's solve the following model using the revised simplex method. In the example, we have the two constraint and three decision variable. So the starting table for the solving problem is as follow. Basically, in this table, you have basic variable s1 and s2, which are slack variable. S1 and S2 is a slack variable, and x1, x2, and x3 is a non-basic variable, which are the decision variable. Matrix B represents the coefficient of the basic variable, while the xn is the coefficient of the non-basic variable. So A is a coefficient, n is the coefficient of the all variable in the constraint, b is the coefficient of the basic variable, which are s1 and s2. Here, this is b, and I is the matrix that we defined earlier, and n is the matrix of the non-basic variable. So x1, x2, and x3 is a non-basic variable, and this is the coefficient of the three variable in the constraint. This is the table for the first iteration of the simplex method. And in this table, xb is x3 and s2, and xn, x1, x2, and s1. Basically, b is a matrix containing coefficient of the basic variable in the starting table, and b inverse and its inverse matrix. The coefficient of the x3, this is the basic variable, it's 3 in the first and second constraint. So let's go to the first table. This is x3 and 3 and 3, the coefficient of the x3 in the first and second constraint. And s2 is the coefficient of the s2 in the first table. So you can see the 0 and 1 as here. Okay, and n is the column, the coefficient of the non-basic variable. And this is the b inverse, the inverse of the b matrix. This is the final table of the simplex method. The matrix B is the coefficient of the basic variable in the initial table. We have the x3 and x2 as the basic variable, and the coefficient of that variable here, x2 and x3, 1 and 2. Okay, the coefficient of the x3 and x2, and n is the coefficient of the x1, s1, and x2 in the initial table. So, and this is the B inverse, and you can see that we have the optimal solution in this table. So let's go to some more general definition of the revised simplex method. Using the above explanation, we can now express the linear programming model in the matrix form. The constraints for this model are written as follows. The variable in the LP model can be classified in two groups on the decision and the slack variable. So this is the decision variable and this is the slack variable. They can also be categorized in the basic and non-basic variable, which is expressed as follows. If we multiply the both sides of the equation here by B inverse, we will have this equation. Since xn represents the non-basic variable and have a 0 value, we have as a result this. Given the B inverse for each table, the above equation here provide the value of the basic variable on the value of the value of the right hand side of the equation for that particular table. By classifying the variable into the basic and non-basic variable, you can express the objective function as follows. This is the objective function. Given that xn denotes a non-basic variable and with the value of 0, you can conclude that the z is an objective function for a special table is equal to C sub B inverse B bar. Using the above relationship, the coefficient of the non-basic variable xn in the objective function is expressed as follows. This is the coefficient of the non-basic variable. Here, this is the coefficient of the non-basic variable, and we define here. The coefficient of the non-basic variable xn in the constraint can be determined as follows. So this is the coefficient of the non-basic variable in the constraint. And the n matrix represents the matrix where each column corresponding to a single non-basic variable. So that is the coefficient of the non-basic variable in the constraint. Each column of the n displays the coefficient of the non-basic variable in the constraint. As a result, you can use the following relationship to determine the pivot table numbers. So this is the column of the non-basic variable for the special table in the simplex method. To better understand the application, we have the following example. We use the this AJ for ratio test we will discuss in the following example. So let's say we want to obtain the value of the simplex table with x3 and x2 as a basic variable. So x3 and x2 is a basic variable. C sub b is the coefficient of the x3 and x2 in the objective function. So Cn is the coefficient of the x1, s1, and s2 in the objective function. B is the coefficient of the x3 and x2 in the constraint. B inverse is inverse. Xn is x1, s1, and s2, and xb is x3 and x2. So what is the coefficient of the non-basic variable in the objective function? So we have this equation, and we will find that the coefficient of the x1, s1, and s2 is 1, 1, 1. In the simplex method, the value of the xb and the z is calculated as follows. So this is the right hand side of the constraint, and this is the objective function is equal to 17. The calculation of the x1 variable column is done as follows. So x1 is a non-basic variable, and we are going to calculate the column between the column below this variable. So it's here. We cover all necessary information to introducing the revised simplex algorithm. Let's proceed the detail of the revised simplex, and we will learn you how we can use the matrix representation for solving this revised simplex methods. So this is the first step. In the first step, we identify the input variable. In each iteration, use here C sub B inverse n minus Cn formula to find the non-basic coefficient in the objective function. If all variables are non-negative, the optimal solution reach, and we have the optimal solution. To obtain the optimal solution, we use here xb is the optimal solution for basic variable, the other is 0, and z is optimal solution for objective function. If any calculated coefficient are negative, choose the variable with the most negative coefficient as the input variable. Step 2 of the revised simplex method involved determining the output variable. To do so, we need the coefficient of the input variable in the constraint and the value of the right-hand side. If xb is the input variable, its coefficient in the constraint can be computed using the following equation. To determine the value of the current basic variable, which is equal to value of the right-hand side, use this equation. The basic output variable is obtained by this ratio test. The basic output variable can be obtained by following minimization, which is called ratio test in the simplex methods. The step of the step 3 of the revised simplex algorithm involving the calculating the newbie inverse for the new basic variable. When it's done, we return to step 1 and pursue the algorithm again. Let's consider the following example as an example and use the revised simplex algorithm to obtain the optimal solution. We have the three decision variable and two constraint, they're less than or equal. So we add the two slack variable as a follow, and we start the revised simplex. In the first iteration of the revised simplex methods, we perform the following step. Determine the input variable. S1 and S2 is a basic variable in the iteration with the coefficient of 0 in the objective function. C sub b is 0 and 0. We need to calculate the coefficient of the non-basic variable xn, x1, x2, and x3 as a follow. So this is the coefficient of the non-basic variable, -4, -3, and -6. Because the coefficient of the x3 is -6, which is most negative value, x3 is chosen as the input variable, as shown in the table below. So we have the 3 value, and the -6, which is belonging to x3, is chosen as the interim variable. In step 2, we determine the output variable. We calculate the coefficient of the x3 in the constraint as follows. Because the smallest value corresponds to the basic variable S1, we select S1 as the output variable. So we do the ratio test, and we will find that S1 is the output variable. And this is the calculation of the rest of the table we need to pursue the revised simplex methods. In step 3, we calculate the newbie and bxp. Because S3 is an input variable and S1 is the output variable, the basic variable for the new iteration is as follows. Let's go to the next iteration. In the second iteration of the algorithm, we perform the following step. Determine the input variable. We calculate the coefficient of the non-basic variable in the objective function. Xn is x1, x2, and s1 as a follow. So you can see that x2 is a input variable because this is the only variable that has the negative coefficient in the objective function. In the step 2, we determine the output variable. We do the ratio test, and you can find that S2 is the output variable because it has a minimum value in the ratio test. In step 3, calculate the newbie and xp. Because x2 is the input variable and s2 is the output variable, the basic variable for the next iteration is as follows. Okay. In iteration 3, we perform the following step. Determine the input variable. We calculate the coefficient of the non-basic variable in objective function, which are xn is x1, s1, and s2. Because all the coefficients are non-negative, they are 0 or positive, we reach the optimal solution. This is the end of the revised simplex methods. The simplex method with the bounded variable is used in the linear programming model where the decision variable have upper bound or lower bound, where uj and lj represent the lower and upper limit of the variable respectively. The treating bounded variable in the same way as the other constraint can be time consuming because the number of the constraint has a significant impact on the computation time. Experience has shown that the computation time increases almost by a third power of the number of constraints. Thus, a more efficient method is required for solving such problem. The method for solving the problem with the variable having a lower or upper bound will be discussed in the document in the website. You can visit our website and learn how we can solve the simplex method with the bounded variable. So If you are really interested in practicing more exercise related to operational research, I invite you to check out my website. There you can find a variety of resources and examples that you help you study in linear programming, simplex method optimization, and any other topics in operational research. You will find plenty of exercise and tools that will be helpful for your research and study. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by form by filling the contact form in our website, which is www.optimizationcity.com. Thank you so much and goodbye for now.